A little hotter. Nope. A little hotter. Nope, nope. A little hotter. Nope. Hotter still. Nope. I'll say this, the fine people at Henkel are extremely modest about the thermal performance of their product. Hello Internet, my name is Quinn and this is Blondihacks. I'm working on the Pennsylvania A3 switcher locomotive this week. We're going to get started on the side rods, which are the first major components of the running gear, all the little levers and things that wiggle back and forth on the side of a steam locomotive that everybody likes to look at. It's going to be a lot of fun. These are really intricate parts. Let's go. Here's our locomotive chassis so far. Now I want to make these side rods that connect the pins here. Of course, the distance between those pins is extremely crucial. We have to get that exactly right. So I'm going to make a jig with this piece of flat bar that I have in the scrap bin. This is a jig suggested by Kozo in the book, and it's extremely clever. You're really going to want to watch this. This is something I would not have thought of. And it's a really useful fixture, I think, for lots of similar types of jobs, even if you're not building a locomotive. The distance between those crank pins will be the same as the distance between the bearings, which is much easier to measure. So that's what we're going to do. And the goal is to make a drilling jig that will allow us to drill holes in the side rods that are the exact same distance apart as the bearings are. Now, even though we in principle know that distance from the drawings and how well we made everything, there's a lot of sources of error in this location. The thickness of the bearings, the exact location of the bearings within the axle boxes, the exact width of the axle boxes and where they're sitting in the frames, all those tiny little sources of accumulated error could add up to where the distance between the center line of the two axles is not exactly what it should be. So it's also a difficult thing to measure. So rather than try to do that, we're going to make a drilling fixture that copies that dimension right from the model. It's really neat, so watch how this works. At one end of the jig, we drill and ream a hole that's the same diameter as the axles. Then I translate down to the other end and put a similar hole at the other end, getting the distance from the DRO so that they're nominally the correct distance apart. These side rods are handed, so just so I can keep track of which side is which, I'm going to mark the outer surface of my drilling jig. Also a great excuse to use this letter punch alignment jig that I made many moons ago, which turns out not to work that well because it turns out letter punches are not that well manufactured. Over to the lathe now, I've got a piece of scrap from which I'm going to make two plugs. One is a static plug that's T-shaped. It has two different diameters, one smaller one and one larger one that is the diameter of the axles or the openings in the main bearings. This static plug goes in one end of the drilling fixture and registers in that to create the first reference that we need to measure the distance between the two bearing center lines. The small end of this needs to be a very accurate fit in one end of the drilling fixture, which it is. Very pleased with that fit. That intentionally sticks through the back of the fixture a little bit for reasons that will become clear momentarily. It's very clever. Now I can part this off and get on to the much more interesting pin at the other end. This is where the real magic is about to happen. That pin we just made is a static one that registers one bearing, but then to register the other bearing, we need an adjustable pin so that we can find the right fit and then be able to copy that fit into the side rods. Importantly, this pin has a hole down the center that is smaller than the tap drill size for the reamer that's going to be used in the final side rods. The outer diameter of this is once again turned to be a very close fit in the main bearings on the locomotive frame. But now here comes the magic. We offset this piece and we turn an eccentric diameter that goes into the drilling jig. Using the dial indicator, I've dialed in roughly 20 thousandths of offset on one axis on the forejaw. And now when we turn this diameter true again, we're going to end up with an eccentric. We're going to have a section of this plug that is eccentric from the main section and also eccentric to the hole down the center of the entire fixture. Much like the other end, this small diameter needs to be a close fit in the drilling jig, which it is. That's looking good. So you can probably see now how this is going to work. I'm going to part this off. Yahtzee. What we've got then is a bushing with an eccentric hole on one side and a concentric hole on the other. And what this does is it gives us a bushing that allows us to move this hole in space relative to the fixture it's in. So that static pin that we made first goes in one end, and then the eccentric bushing goes in the other end. And now look at the magic here. We can rotate that eccentric bushing and it will change the distance between those two holes by up to 20 thousandths. So all we need to do now is rotate that bushing a little at a time by trial and error until both of those bushings fit perfectly into the main bearings, and we now have a drilling fixture that will create two holes the exact right distance apart. Once we've got that, I mark it on both the fixture and the eccentric to make sure that nothing moves. Then I test fit it on the other side to make sure both sides are the same, which fortunately they are. I guess I did something right in manufacture there. Then I go back over to the bench and I can Loctite that eccentric bushing in the correct position using the marks that I made. This is such a clever thing. It's such a nice idea. It's something I never would have thought of. And it's one of the many, many reasons why Kozo's books are such a good read, even if you're not a locomotive person. Tricks like that are just so good to have in your toolbox. These side rods are going to be made from 4140. It's a very nice free machining steel, extremely strong. It doesn't need to be this strong for this application, but this is actually the only free machining steel I could get in the dimension of bar stock that I wanted. And they're still over thickness, so I'm going to have to thin them down a little bit. Now, as I've talked about a lot on my channel, cold rolled material does have internal stresses in it that can be released when you machine it. It's most noticeable when thinning down or making deep cuts in thin bar stock like this. There's a chance the material will banana after it's machined. Now, it doesn't happen all that often, and usually only when you're removing a substantial percentage of the material. I'm only making a light skim cut on both sides to thin it down a little bit, so I wasn't very worried about it, and I didn't have to take any precautionary steps here. If you are worried about it, you can do something called normalizing, which is a process that I'll cover in some other video when it becomes necessary, but really wasn't necessary here because, again, just taking a light skim cut, and I'm cutting on both sides to help equalize those stress releases. I stopped once I reached the thickest dimension on the side rods. These side rods are actually tapered in multiple dimensions. They're a very complicated piece, but for now I'm going to bring these blanks down to the thickest dimension on the entire rod. Now I'm going to get centered up. Even though these blanks are actually rough cut, at this point I want the holes roughly centered on the blanks to make sure I have material all the way around the holes to clean up. Now Kozo suggests doing the holes now because they're going to be useful for fixturing, and it also is a handy way to make sure that we've got the distance between the holes correct before we put in the many, many hours of work that are going to go into these rods. These rods are very intricate pieces, and there is a lot of hours of machining in them, so the sooner we know if our jig is correct, the better. Speaking of which, here is that jig. Remember, this first pin is over length, and the eccentric pin is not. The eccentric pin is below the surface. So what that allows us to do is drill and ream one hole on one end of the side rod, push that pin into the jig, and then align the drill on that drill bushing on the other end. Remember, this bushing was the eccentric one that's now Loctited at the correct distance, and it's now acting as a drill guide. That's why it has the hole in it. I get well aligned on that bushing, and then I always like to start the machine with the drill in the bushing so that you're not passing the cutting edge through it, which tends to chew up the drill bushing. We only have to use this twice, and it is steel, so it would probably be fine, but it doesn't hurt. Now this drill size is smaller than the pre-drill size for the reamed hole that we actually need. There just wasn't enough physical space, I'm sure, in Kozo's design to go straight to the pre-drill size, but that leaves us with an extremely accurately positioned pilot hole, and now we can come in with the pre-drill size for the reamer, and it's going to follow that pilot hole so we don't have to worry about positional accuracy from here on. And of course we follow up with the reamer for the final dimensioning. Looking good, but while I'm set up on this hole, I want to do one more feature. This end of the side rod is the front, and the front, you may recall, has these big T-pins that retain the rod on the crank pins. And we need a counter bore to recess those pins flush with the top surface of the side rod, because the outer main rod has to clear this rod. Now, a large counter bore is very, very similar to a spot face. There's sort of a gray area between those two features, And I actually have a spot facing tool that I made for my die filer project to spot face the mounting bolts on that casting. This tool is actually already very close to what I need. It's got a nice tool geometry on it for counterboring or spot facing, but the mandrel on it is a little too small for this application. It needs to be well supported in that bore. So I decided I can just adapt this one, and that'll be quicker than making a whole new spot facing or counterboring tool. I decided to run over to the lathe and make a little bronze bushing that will take up the difference. And as a nice side benefit, it will do less damage to the bore that it's going to be running in during the operation. I happen to have a reamer that's the same size as the shaft of that tool, because of course that shaft was made to be a very close running fit in the screw holes on the die filer, which was a standard dimension. You'll note I do the final turning after the drilling and reaming, because drilling and reaming on a really thin bushing like this can actually stretch it, and it might come out oversized when you're done. That's a perfect fit on there. So I will Loctite that onto the tool so it spins with the tool, and that's going to ride in the bore like so. And you can see how that little tool bit is going to cut my spot face or counterbore. Now that tool is much too long. We need a much smaller counterbore in this case. I tried to adjust it down, but there just wasn't enough adjustment room on that tool to do it. The tool was much too big. So I went over to the D-bit grinder and I ground a new little tool bit that's shorter. In this way I have multiple tool bits and more range of counterbores that I can do with this existing tool. This is why you always keep your custom tools that you make for an operation, because you never know when you might need to do a very similar operation in the future. I also shortened this tool a lot. It was very, very long specifically for the die filer casting, but wasn't very rigid as a result. And away we go. Look at that. That is just cutting beautifully, which means A, I pretty much got the tool geometry mostly right, and B, this is 4140, which machines absolutely beautifully. I really, really like 4140. It's a lovely, lovely steel. It's surprising how free machining this stuff is. This is a very high tool pressure operation, and it's cutting like butter. 4140 is among the strongest of steels. Like the output shaft on a D10 Caterpillar is going to be 4140. That's how strong this stuff is. But it's also heat treatable and somehow free machining. I don't know, it's Metallicor, the god of machining's personal steel. It's magical. See how I did on fit? Oh, look at that. First try. Gotta like that. Depth is just right, and there's a little bit of clearance around it so it can move around. I don't want it to be over-constrained on the crank pin. And that is really, really nice. So that's good. I've got everything adjusted right, and I can do the other side rod with this same setup. So that's one rod blank. Now I just got to do the same thing on the other one. And just out of curiosity, I'll check and make sure that it didn't banana, because as I said, it was cold rolled and I machined some off, and I'm sure it's fine. Oh my goodness, look at that. That is a dramatic banana. That is so much more distortion than I have ever seen from removing that little material off of something this thick. At this point, I could try to straighten this, but I honestly don't have very many hours invested in this part, so I just decided to scrap it and start again. And well, remember that hypothetical process called normalizing that I was hypothetically going to show you someday? That day is today. There are no mistakes on my channel, only pedagogical opportunities. Normalizing is a heat treating process that removes the internal stresses in material. It's actually the same as annealing. You simply heat the parts up to glowing reddish-orange heat and then let them cool down slowly and naturally. You usually want to avoid doing this for yellow metals because it anneals them and weakens them at the same time. With steel that's already soft like this, however, it doesn't get weaker, so there's really no reason not to do it other than inconvenience. And as you can see, that's now still straight after doing that, but it won't have any internal stresses in it, so we can machine these new parts with no risk. Just to prove that point, here's that piece thinned down now, and you can see that it's nice and straight still. So, normalizing for the win. Don't be lazy like I am. Normalizing steel is never a bad idea, especially for thin parts like that. Now I'm going to make the bearings next, which is kind of skipping ahead a little bit because we won't need the side rod bearings for a very long time yet. But I want to make them now so that I can test fit these side rod blanks and make sure that everything's going to work the way that I hope. Once again, trying to minimize risk before I put many, many hours into the rest of the manufacture on these side rods. For the bearings, I pre-drilled them, and then I used a really tiny boring bar that I ground recently for another job. It's coming in very handy on things like this to get maximum concentricity on these bearings, and then I finish with a reamer to bring them to dimension. with the ID on dimension, and then I do the OD after the fact, which is backwards from how I typically do it, but just like the counterboring tool, this is going to end up being a very thin bearing when we're done, and the drilling and reaming can actually stretch them out if you have a thin wall when you do those operations. We actually need 4 of these bushings in 2 different lengths, so it was pretty easy to make them in batches of 2. All the dimensions are the same except length, so that's pretty easy. I made them 2 at a time so that I had minimal stick out while I did them. That's a really beautiful fit on there. That's good. That will eventually be Loctited into the side rod, and we'll be running on the hardened crank pins to form a nice bearing. Yahtzee off a pair of those, then do it all again to get 2 more, and we will have our 4 bearings. Two of the bearings are shorter because the side rods are thinner at the front than they are at the back because of those counter bores for the big T-pins. Well, they certainly look the part. Let's see if they actually fit. Big moment of truth now. One of them will go on, of course, because the wheels can simply rotate as needed to make them fit, so that's not a concern. The real test comes when you try to put both of them on. That's looking good. We'll get the other side on. Here goes nothing. Let's see if it rotates smoothly. And no, it doesn't. Poop knuckles. There's a pretty major tight spot at front dead center on one of the rods. And that does not feel like something that's going to break in. This isn't just tightness from things being new. This feels like serious binding. Something is not right. If I roll it back and forth, you can really see the effect. The wheels completely bind up at one point and they just start sliding because the side rods are totally bound up. So that should definitely not happen. I did a bunch of diagnostics here to eliminate some variables. Switching the rods makes no difference. Everything is smooth with only one rod on either side, and either rod can be on either side and everything is smooth. Things only get bound up with both rods installed, regardless of which rod is on which side. So all of that means I think the only problem can be that the axles are not quartered the same. At the tight spot, the binding occurs because the distance between the crank pins in that moment is different on one side than the other, and that can only be caused by quartering. Which, if true, is unfortunate because that's difficult to fix, but let's verify that hypothesis. I put the chassis on the surface plate, and I've got one crank pin at top dead center, and then I measure the height of that. Then I measure the height of the quartered pin on the other side without moving anything, and making note of all those measurements for the front axle. Now, of course, you can do a bunch of math and figure out what the angle between those pins is from here, but remember, it doesn't actually matter what the angle is very much. What matters is that the angle is the same on both axles. So I don't have to measure the angle, I just have to measure those 2 heights, then flip the chassis around, take those same 2 measurements on the other crank pin, and if the axles are quartered the same, the measurement should be the same. If one pin is at top dead center, that top dead center height should be the same, and the 90-degree pin on the other side should also be at the same height front to back. And they are not. So the 2 top dead centers were the same, they're within 1/1000th, that's good. But the side pins on the other side were consistently about 25/1000ths different. So one of the 2 axles is definitely quartered differently. Then the question becomes which one is right. You could do a bunch of math again to figure out which one is closer to 90 degrees, but math is hard and I'm lazy, so I just drew it up in CAD with those measurements that I took and found that indeed the measurements that I took match for the front axle. So the front axle appears to be correctly quartered and the rear axle is not correctly quartered. It's always good to verify with a different line of evidence, so I put the axle assembly back on the quartering jig, and of course the crank pins are now facing outwards, so I can't actually line them up in the jig the way they're intended to be used, but I can do a visual inspection. I can line up one pin visually with the reference surface, and then flip the axle set around and inspect the other side. Here's what I mean. You see how this pin here is sitting right on the reference surface. And if I carefully spin the fixture around without moving anything and sight down on the other crank pin, look at that. That crank pin is definitely below that reference surface. And 20,000ths of error is luckily enough that I can see it with the naked eye, and that is definitely inside that surface. So this confirms my suspicion that it is the rear axle set that is incorrectly quartered. Now, how to fix this? I considered modifying this jig into something that would allow me to quarter the wheels with the axle set assembled like this, but that was going to be a lot of work, a lot of modification, and it might be less accurate of a result. Then I looked at the Henkel website and looked up the performance data sheet of Loctite, and actually Loctite fails at around 200 degrees Celsius. The strength drops off fairly linearly with temperature, and around 200 it fails. And 200 degrees is well within the range of a toaster oven. So what I think I can do is just put the whole axle set in the oven, heat it up to break the Loctite, and then take it all apart and reassemble it just like I did before using the same fixture. Now they are of course painted, and I don't want to damage the paint, but this paint that I used happens to be engine block paint, engine enamel, which is good up to 260 degrees Celsius. So it should be fine in the oven. It shouldn't get hurt by this process. I didn't want to use a torch for this because it's very, very easy to overheat things with a torch, and it would be very easy to damage the paint. And a torch is also going to discolor the surfaces that I've spent so much effort polishing. I really don't want to have to fix all of that. So I just put it in the oven and heated it up until it was at 200 degrees, and this Loctite should break free. The Loctite should just break free. I'll heat it up a little more, and I need bigger gloves now because it's getting very hot, and that should just break free because it's at a little bit of tapping. So this Loctite is at 200 now, and the data sheet says it should just break free now. So yeah. Loctite is very impressive stuff, and it would not get loose. I even let it cool down because I thought, well, maybe the stainless steel axles expanded more than the cast iron did. But no, even after cooling down, these things are still very stuck together. But I reasoned that surely the Loctite has been weakened by all of that heat. It certainly should be. So it's probably now going to be a fairly light press fit at least. So I can press them out of there, hopefully. Don't want to press too hard on these because cast iron is brittle and it's very easy to break it doing this. So I've got it well supported right behind the hub where I'm pressing. There's no force on the rim or on those spokes. And sure enough, it was a very light press fit to get it out of there, like maybe 100, 150 pounds. Very easy press. So the Loctite has definitely been compromised by that heat. It just didn't quite want to let go. Here's the residue of that Loctite. I was already impressed with this stuff, but now I'm extremely impressed. I had it heated up to a good 250 degrees Celsius, and it was not letting go. Those were slip-fit axles, and they would not come off, so Loctite, good stuff. The crank pins did come out easier, I will say. I may not have prepped those surfaces quite as well. But now I can redo the process that you saw in an earlier video to quarter these wheels. Everything's all been cleaned up, everything's spotless once again, surfaces properly prepped for Loctite. The worry at this point is that I'm going through the same process again, the same thing I did before, and just hoping it's going to work this time, which I think is some sort of definition of insanity. However, I really don't know what else I can do. I mean, this jig really should work. I think it can only be the case that I did something wrong the last time I did it, and I'm just doing it extra carefully this time. Once that Loctite had set, I did the surface plate measurements again, and sure enough, now that's within a couple thousandths of the front axle, so I definitely got it better that time. I don't know, again, what I did wrong the first time. Maybe something moved, maybe the Loctite wasn't fully set, I don't know, but the quartering should be much better now. Let's put the rods back on. And survey says, oh, magic. Magic, just like that. Perfectly smooth throughout the entire rotation. That was exactly the problem. That's a relief, because if that hadn't fixed it, I don't know what plan B was. I didn't know what else might have been wrong. But that has definitely solved the problem. That rolls beautifully now. That's great news, because now I can proceed with all the rest of the machining on these parts, confident that the distance between the holes is good. Now, there's always a chance that those parts could bend again, because we are going to be removing a lot more material, but in principle, they're well normalized, so they shouldn't. But, all we can do is proceed and see how we get along. This is the order of operations that Kozo recommends, so that's why I went this way. And I'm really glad to have been able to verify the distance of those holes, verify the drilling jig before putting in many, many hours of work on the rest of these rods, and then potentially having to scrap them after all of that. This went really well, all things considered. I'm really happy with where we're at. I didn't get as far into the side rods as I would have liked because of all the challenges, but it was an interesting exercise anyway, and we've got a good start on things. It's getting more trainy by the day. Thank you very much for watching. Thanks to my patrons for making all of this content possible. And I will see you next time.